In this video, I'm going to talk about the mean value theorem. This is how the mean value theorem goes. Let's say you have a function f. F has the following properties. Number one, it's continuous on the closed interval ab. Number two, is differentiable in the open interval ab. Now, if these two conditions are satisfied, then we conclude the following. Then there exists a point C in the open interval AB such that f prime of C is equal to f of B minus f of A divided by B minus A. So, what does this theorem tell you? If a function is continuous on a closed interval and differentiable in the corresponding open interval, then there is a point, or there exists a point C in the open interval such that f prime of C is going to be equal to f of B minus f of A divided by B minus A. You can think of that as a kind of like average also over that interval. So f of B minus f of A divided by B minus A, this is kind of like the average of the function in that interval. So that's where I guess the name comes from mean or the average. Now how do I show it? To show that, what we are going to do, we are going to kind of use the Rolle's theorem. Now, Rolle's theorem is very, very similar to the mean value theorem. So, if you have a function that's continuous on closed interval AB, like this one right here, and differentiable on the open interval, exactly same conditions as the mean value theorem condition, right? However, with an additional condition that f of A is equal to f of B. That means the function values are the same at the boundary points B and A. If that is the case, if these three conditions are satisfied, then there exists a point C in the open interval AB such that f prime of C is going to be equal to 0. Now we are going to use this Rolle's theorem to prove the mean value theorem. So we are going to devise a function in a way so that we can use the Rolle's theorem. So let's say you have this function. So this is your y and this is your x. Let's say you have this function, something like this. Okay. Now, let's say this is point A, and let's extend this guy. Let's say this is point B. So our function f, so this is my f of x, is continuous in the closed interval AB, okay, closed interval AB, and is differentiable in the open interval AB. Now we need to show that f prime of C, there exists f prime of C such that this condition is satisfied, or this equation is satisfied. Now, what we are going to do, we are going to go ahead and label these points, let's say point A and point B. And I'm going to draw a straight line. Maybe I can use a different color here. So let's say this is my straight line. Okay. Now what I'm gonna do, create a special function, okay, in a way so that it satisfies the third condition of the Rolle's theorem. And the way we do it is by taking the difference of f of x and the straight line. So let's say this is a point x, okay? So at this point, so I'm going to take the difference of f of x and the straight line. So there's going to be just this little line segment. Now, to find the equation of a line, you probably remember y minus y1 is equal to m times x minus x1. Okay? So what is my x1 and y1? x1, y1 is a point, fixed point. x1, y1 is a fixed point. So I'm going to just take this point. At this point, the coordinates, as you know, x coordinate is a and y coordinate is f of a. So this is the point. And at this point, you also know x coordinate is b and the y coordinate is f of b. Now, I'm going to use the left point, which is a comma f of a. So that's my fixed point. Now, to find the slope of the straight line, you know that the slope of a straight line is m is equal to y2 minus y1 divided by x2 minus x1. Okay? So now, what is my y2 and y1? So let's call this one my y2, x2, y2, and this one is my x1, y1, which I already labeled right here. So what is y2 minus y1? y2 is f of b minus f of a divided by b minus a. That is the slope. So once I know the slope and I know a point, I can find the equation of a straight line, and that is the equation. So y minus y1, remember my y1 was f of a, is equal to slope f of b minus f of a divided by b minus a times x minus a. So x minus x1, x1 is a right here. Now, if I simplify it a little bit, this is what I get. So I just move this f of a to the right, and this is what I get. So this is the equation of the line L. So let's call it L. All right. Now, I'm going to go ahead and define a new function. Let's call it g of x. G of x is going to be very simple. F of x minus the line L. Okay, this is the line L. But my line L is nothing but this. So g of x is equal to f of x minus all of this, which is f of b minus f of a divided by b minus a times x minus a, then plus f of a. So if I distribute this negative, that's going to give me negative f of a. So this is the function. Now, this is a special function that I have kind of devised. What it is a linear combination of the given function f of x and the line. That's a fancy way of saying that I subtracted L, the line, from the function. So that's what's going to give me this little line segment. So I'm taking the difference of two functions. So now look, straight line L is continuous on the closed interval and is differentiable in the open interval. Okay, it's continuous on the closed interval AB and differentiable on the open interval AB. And so is f of x according to the assumption. So the difference of these two functions, f of x minus L, it would still be continuous and differentiable on the corresponding intervals. So that is what it is here. So some sort of linear combination of two continuous functions will still be continuous, right? And in this case, differentiable functions will also be differentiable. So having said that, now look at this function g. A couple of interesting observations. What is g of a? So that means what is the value of this function at this point where a. So it's my g of a is going to be f of a, I'm just plugging in the value of a for x, minus f of b minus f of a divided by b minus a times x is a, that's what it is, so a minus f of a. This becomes 0, right? This becomes 0, so the whole term disappears. Then you have f of a minus, so this is a minus, f of a minus f of a is going to be equal to 0. So how about g of b? Let's try this. So I'm just going to replace here, for x I'm going to replace b, so it's going to be f of b minus f of b minus f of a divided by b minus a times x minus a, x is b minus a minus f of a. And b minus a is gonna cancel out. Then you're gonna have negative f of b minus f of a, so which is gonna give you negative f of b plus f of a. So actually let me write it down. G of b is gonna be f of b minus, now if I distribute this negative, I'm gonna have f of b, and negative is gonna make it positive, f of a minus f of a is equal to 0, because this cancel out. Oh, by the way, we just found out that g of a is equal to g of b. So this new function g of x that I have devised, this has the third characteristic or third contingency that is being satisfied. So third contingency in the Rolle's theorem is that at f of a and at f of b, the function values must be the same. In this case, my g of a and g of b are the same, and both of them are equal to 0, by the way. I just showed it to you here. So for this function g of x, the Rolle's theorem must hold true because it is continuous in the closed interval, differentiable in the open interval, and f of b is equal to f of a. So therefore, by Rolle's theorem, there exists a point C in the open interval AB such that f prime of C is equal to 0. In our case, it's going to be g prime of C. That's going to be equal to 0. So we are going to have a point C in the open interval AB such that g prime of C is going to be equal to 0. What is my g, which is this right here? So I'm going to take g prime of x. So g prime of x, so look at this, is going to be equal to f prime of x minus derivative of the second term, f of b minus f of a divided by b minus a, that's a constant. And the derivative of x minus a is just 1, right? So we don't need to worry about it. Then derivative of f of a is 0. So this is the derivative. So according to Rolle's theorem, I should have such a point such that g prime of c is going to be equal to f prime of c minus f of b minus f of a divided by b minus a, and that is going to be equal to 0. That's the conclusion of the Rolle's theorem. Now if I rewrite this part, what do I get? F prime of c is equal to f of b minus f of a divided by b minus a. That, by the way, is the exact conclusion for the mean value theorem. Okay, so this is what we are trying to show in the mean value theorem, as you can see right here. So we just showed that given that a function is continuous on the closed interval AB and differentiable in the open interval AB, then there exists a point C in the open interval AB such that f prime of C is equal to f of B minus f of A divided by B minus A. This proves the mean value theorem. So, just to summarize, we use the Rolle's theorem to prove the mean value theorem. So, you need to know Rolle's theorem first before you can prove the mean value theorem, or at least assume the Rolle's theorem, which has three conditions: continuous on the closed interval AB, and differentiable in the open interval AB, and at boundary points A and B the function has the same value, that is f of A is equal to f of B. If these three conditions are satisfied, then there is a point C such that C in the open interval AB such that f prime of C is equal to 0. And to satisfy the third condition for Rolle's theorem, we devised a special function called g of x, which is the difference between the f of x and the secant line from A to B. Okay, so that means we use the equation of the line from point A to B and subtracted it from the given function f of x, and we use the y minus y1 is equal to m times x minus x1, and found the equation of the line and subtracted it. And then at that point we showed that this new function that I have devised is actually holding the Rolle's condition number 3 true. That means g of B is the same as g of A. Then I apply the Rolle's theorem and come to the conclusion for the mean value theorem. I hope that this discussion was helpful. Thank you very much.